Hello guys, my name is Hamzah Sarwari, and today I'm going to be talking about autonomous vehicles with Aryan Patel. So when it comes to autonomous vehicles, there's different autonomy levels, which indicates how much automation a vehicle uses. So level zero is basically absolutely no automation, which is very common for older vehicles. So meaning that there's no cruise control, there's no lane keeping assist and whatnot. And with level one, that's where you begin to see that. So you'll have cruise control, you'll have emergency braking, you'll have and lane keeping support. Um, it's very common for newer cars nowadays to have that. And then level two and three is more of where Tesla is today. So vehicles are able to, steer and accelerate, brake by themselves under certain condition, but it still requires a driver to have their hands on the wheel. And then level four is a higher automation. So the vehicle is capable of doing almost all of the driving tasks by itself, but it still does need a driver behind the wheel and it needs a driver's attention. And then level five is full automation. So no driver is needed at all. And when you hear companies such as Google talking about their autonomous vehicle technology and things that they're doing with autonomous vehicles, this is pretty much what they're referring to. So no driver behind the wheel. And so an autonomy overview of basically the different components that goes into a self-driving system. So first we have a map. Mapping is something that all self-driving vehicles require, right? So these vehicles need to have some sort of map to determine what's around them. Next, we have route planning. So this is important because if a car is going to drive by itself, it needs to know where it's going and what its destination is, and what is an optimized route to take. Next, we have perception. So what is the car perceiving, or what is it interacting with? So is it coming across a stop sign, a red light, a pedestrian, or other cars? These things are always changing. So the car should be able to perceive these things and intake information by what's around it. Next, we have localization. Localization means where is the vehicle exactly? So which street is it on and where on the street is it? Next, we have prediction. So prediction is used to predict the moves of other road users, such as cars, cyclists, and pedestrians. We want to be able to know if a person is gonna cross a street or if a car is gonna make a left turn or a U-turn, or is it gonna go straight. And this is important because cars are always moving, right? And we don't really want to know what a car is doing right now, but we want to know what a car is going to do. So that way we could predict what the autonomous vehicle should do. So what upcoming moves it should make and how it should react to the moves of other vehicles and other road users. Next, we have behavior planning. So this basically takes in everything that we've discussed so far and combines all of that information to make a behavior or make a plan for the car to make. And with that, we have trajectory generation. So this is the vehicle's planned trajectory, right? So what is it going to do? Is it going to swerve left? Is it going to swerve right? Is it going to speed up? Is it going to slow down? And it's going to implement the behavior that it has planned. Finally, we have control. So control is basically putting everything together and knowing that the trajectory that the car is going to make, we want to send it through the car's controls, right? So are we going to turn the steering wheel slightly, or are we going to turn it a lot? Are we going to accelerate? Which pedals are we going to use? Are we going to use the brakes? Are we going to use the gears? And although this might sound like the easiest part, this is actually not that easy because we want to make sure that these cars are making smooth moves in case there's other passengers in the car, or for other cars that are around the vehicle, because we don't want the car to make a sudden stop or a sudden lane switch, and that could be dangerous. So these moves have to these moves have to happen smoothly. So with mapping, we have a type of map called semantic maps, which is a high definition map that is specific to autonomous vehicles that contains images to the centimeter level. So it's not like your typical Apple or Google map, but instead it knows exactly where the lines and curves are down to the centimeter level. And this is so vehicles that are making its moves and turns and whatnot, they're not hitting other, objects, or they're stopping at specific lines, and they're not crossing lines or crossing, lanes. And it also knows the precise location of traffic lights. And this is important because if a street has multiple traffic lights, the car will know which exact traffic light it's supposed to respond to. So even if there are two traffic lights facing a vehicle, let's say one of them is just for cars that are turning left and the car's not in that lane, it'll know, okay, I'm not supposed to move even if that traffic light does turn green. And this is important for level 4 and 5 automation because it also maps out speed limits and restrictions that are placed in a specific area, right? So for example, if a car is parked and the map knows that the cars are supposed to be parked here from 9 a.m. to 5 p.m., the car will predict that. So it won't register this as a stop car. Instead, it'll register it as a parked car. So it's not going to move behind it and get stuck there. So the next type of mapping we have is called LiDAR mapping, which is light detection and ranging. So this basically is a spinning laser that is hitting objects, and those lasers are bouncing back. And then depending on how long it takes for those beams to bounce back, we could determine how far the objects are. And it even goes to being able to sense the types of objects that are nearby. So depending on the strength of a beam, for example, a weak beam that's bouncing back will allow us to determine, okay, well, that was a dark object. And if the beam comes back strong, we can know that this was a light object. These LiDAR maps create a bounce map. And every time a spin takes place, which is approximately 100 times per second, the vehicle is storing this information as the car moves. And it maps these coordinates with the objects that are nearby. And almost all cars use LiDAR or semantic maps. And they create these maps beforehand. And this is why self-driving cars don't take streets or routes that they haven't used before or they haven't mapped out yet. Route planning. So like I just mentioned, these autonomous vehicles don't take streets or paths that they haven't taken before. So they create optimized routes for themselves to take, which is pretty much the same way when we use Apple or Google Maps. We're given like the fastest way to go to a specific destination. However, for our autonomous vehicles, they come across many, many different circumstances. So, for example, traffic and accidents and constructions, they need to know how to deal with these circumstances. But the smartest thing for them to do, instead of, going to a specific, if there's an accident or construction, instead of, going there and trying to figure out what move it should make or, what to do to deal with that situation, the smartest thing to do is to just avoid that situation. And so it could optimize, a route that will avoid those circumstances. These routes also include instructions for, which lane the car needs to be in. So for example, if we know that there's going to be a right turn coming up in half a mile, the car should be in the right lane to make that turn. So it doesn't have to make any last minute moves. Next, we have perception. So there's 3 different ways these vehicles could know or perceive what is around them. First, we have camera. Cameras, as we know it, they just see what's in front of them and they take information from that. And if we use 2 cameras, we could create some sort of 3D map. Next, we have radar. Radar, which is kind of like the least helpful. It just kind of determines if things are coming the vehicle's way or if it's moving away from the vehicle or kind of in which direction are they moving. Next, we have LiDAR, which is, as we discussed, lasers being sent out and bouncing back and taking information from the beams. So autonomous vehicles use sensor fusion, which combines the data from all 3 sensors to improve their recognition. And then it sends this data to a convolutional neural network to recognize the objects, right? So it's going to send the object, it's going to send the data to the network, and the network is going to say, okay, well, from the data, we know that this is a car or this is a person. And so once the network recognizes an image and it says, okay, well, this is a car or this is a person, it's then given an ID using the Kalman filter. This is important because the autonomous vehicle is going to detect many cars and many objects, but it has to identify, hey, was this the same car that we detected 10 seconds ago, or is this another car? So when it comes across a vehicle, it's going to give it an ID, and then it's going to, as the car is moving, it's going to, continuously detect that vehicle or detect that pedestrian or detect that, you know, stop sign, and because it has a identification, it is you know, able to do calculations such as velocity and acceleration because it knows that these are the same vehicles and these are the same objects that are moving. Prediction. This is used to predict the behaviors of other moving vehicles and pedestrians and moving objects. Um, this is used for the vehicle to plan out their upcoming behaviors and upcoming moves. Over here, we have a prediction map. And if you guys could see, the darker shade is the oldest movement and the lighter shade is the most recent movement. And then these over here are used to predict the likely future trajectories, right? And these ellipses, these are used to show uncertainty in predictions. So the larger the ellipse becomes, it means the more uncertainty there is. The vehicle then uses probabilistic reasoning to, you know, generate their next move. And for example, over here, if you look at the diagram, we have a car moving right, and because we know that the car's wheels are turning right, we have the probability of it making a right turn. And as it goes on, the chances of it are the chances of the vehicle to turn right are more, you know, probable. However, there's still a possibility that it could go straight. So just because it's about to turn right doesn't mean that last minute it's not going to turn straight. So there's that slight probability that this could still happen. And now I'm going to pass it on to Aryan.
So I'm going to talk about localization and why is it important for autonomous vehicles to have pinpoint localization. And then I'll go into a little bit more depth to explain one of the key techniques that is used for localization. So let's talk about localization in a little more depth. When we drive a car, we usually use a GPS or a Maps app to know where a car is. But GPS actually has an accuracy of 1 to 3 meters or sometimes even more. This wouldn't work for a self-driving car since this is a width of a lane and the car can drift off from its lane, which can be dangerous and lead to accidents. A self-driving car needs to have a much higher accuracy, even less than 10 centimeters. So there comes in localization. Localization means knowing where am I, and this is critical for a self-driving car as at every instant it needs to know where in the world it is. There are many different techniques or algorithms to help an autonomous vehicle locate itself. And all of these techniques come under the general umbrella of the term SLAM or simultaneous localization and mapping, which basically means that we have to pinpoint ourselves in the surroundings by referencing our positions with other objects or landmarks in the same surrounding. Some of these techniques are odometry, Kalman filtering, or particle filtering. So what happens in a particle filter? In a particle filter, we create particles throughout the area defined by the GPS and we assign a weight to each particle. The weight of a particle represents the probability that the vehicle is at the location of the particle. Here we have a video showing a particle filter in action, tracing a car in a simulated environment. The circular points are the landmarks in the map. The green lines are the laser sensors from the car to these landmarks, and the blue circle is the closest particle that is tracking the car. We notice how closely the particle tracks the actual car. The implementation of the algorithm used in particle filtering is according to the following scheme. We distinguish 4 different stages, which include initialization, prediction, measurement, and resampling. This is usually realized with the help of several data from GPS, IMU, speeds, and measurements of the landmarks. So here is how a particle filter actually works. To begin with, we have a map of the world. The map has landmarks which could be houses, buildings, lampposts, etc. And we know the location of these landmarks within the map. First, we initialize our map with n number of particles randomly placed around the map. Think of these particles as possible location of the car. In the beginning, we don't know where the car is in the map. So all particles are given equal weight, meaning that they all have equal probability of representing the true location of the car. Second, at each time step, the car moves. Our sensor gives us information of the velocity and the angle in which the car is moving. We move each of the particles by the same distance and in the same direction as the car. This is called the prediction step. Third, now comes the measurement step. In this, using the LiDAR sensor, we measure the distance of the car to the known landmarks on the map. LiDAR uses laser for measurement and generates a point cloud of the world around it, providing the car with fairly accurate position X and position Y values. However, one of the disadvantages of using LiDAR in this case is that it is not very accurate in poor weather conditions or if the sensor gets dirty. There are certain things that we need to take care of when applying the LiDAR measurements. Like data association, multiple LiDAR measurements can be associated with each landmark. If that's the case, we use the nearest neighbor to choose the closest LiDAR reading to a landmark, as a LiDAR reading as shown in the image. Transformation. When LiDAR measurements are taken from the car, their X and Y positions will be with reference to the car, which is called the local coordinates of the car. These need to be converted to the global map coordinates by also taking into consideration the position of the different landmarks. Finally, in the fourth step, we resample particles such that particles with higher weight and hence higher probability to be close to the true location of the car are picked, and those with the lower weights are dropped. The cycle is then repeated by going back to step 2 with the most probable particles. We take into account our displacements since the last computation and realize a prediction, then a correction according to our observation. Through this process, we see that particle filters are very effective and can locate a vehicle very precisely. For each particle, we compare the measurements made by the particle with the measurements made by the vehicle and calculate a probability or weight. However, some of the downsides also need to be kept in mind. This calculation can make the filter actually slower if we have a lot of particles. Also, it requires having the map of the environment already ready where we drive permanently.